Hi everyone. Welcome to MathSpellBook. I'm your host Peter, and we are going to get back into basically doing some physics problems today. So I think we have like only just two. So I just did a problem like this morning, but unfortunately I got it wrong as well. Because the thing of it is that I think the harder relativity problems get, I think what's making me struggle, I think what's making me kind of like unsure about myself with these problems is that when it involves like trigonometry and like actually like two dimensions, that's when I get a little bit flustered, because I have to think about the angle, I have to think about how the system is working, because like I also have to think about how to envision the forces as they impact like something else. So like if a wind is impacting like a flying plane, I have to think about like where to put the vector for the wind and where to put the vector for the plane. And sometimes like when I do it in the wrong way, it just like doesn't work out. So that's basically, I guess I discovered that gap. So now I'm actually going to implement my implement this new way of thinking. And I think that's the thing that I have to actually practice with. So I think we're going to just try to practice relative velocity problems until I can actually fully understand how to think about them without having to develop the mental muscle. So that's basically how I plan to go about it. Let's see. An airplane pilot wishes to fly due west. The wind is blowing towards the south. So we have a plane that's flying due west this way, and a wind blowing towards the south. So maybe we can just draw it like this, because the wind is going to impact the flight path. So I think so the wind relative to the earth is blowing at 80. Wind relative to the earth is blowing at 80 kilometers per hour. So if we convert that, so it should be like 1,000 meters per kilometer. So times 1,000, so around 80. I mean, do we have to convert it? I feel like we should though. Actually, I want to convert it to meters per second, because I don't want to have to deal with like, because I think it's because I'm just a stickler for units. So I think we'll just convert it on the other side, because we're going to have to deal with a lot of stuff here. So 80 kilometers per hour. So 1 kilometer is 1,000 meters, and 1 hour is seconds. So divide that by, gives us 22 meters per second. Okay. So if the airspeed of the plane is, okay, so the plane to the wind is 300 kilometers per hour. So we can just do the same thing we did here. Meters, kilometers, 1 hour. 88.9 meters per second. In which direction should the pilot head? If the airspeed of the plane is 320 kilometers per hour, which direction should the pilot head? What is the speed of the plane over the ground? Illustrate with a vector. Okay. Maybe we can draw a picture of the plane here. It's not a great drawing, but we'll just draw it like that. Okay. So wind is blowing due towards the south. Hey Hans, what's the best part of your day so far, my friend? So for question A, now the way they ask the question is pretty weird because it says, in which direction should the pilot head? The pilot wishes to fly due west, so basically we have to make sure that he continues to maintain a west trajectory. Finding a Minecraft server with my favorite Minecraft mod. Oh, nice, that's good. Glad to hear that. Or read that, I should say. So we have to make sure that it maintains. So it's going to be similar to the problem that we did, I think, the last time involving angles. So if it's pointing south, we have to make sure that the plane is actually going upward. So it has to go basically the same. I think it has to match the same velocity as this, but going northward, or at least the y component of this, the y component of the plane's flight path. So the equation we have is the plane relative to the Earth, and so we don't know exactly what direction the plane should be taking, plus wind relative to the Earth. Movement is about perspective, right? So if we have two things in an empty universe and one is moving and the other isn't, from the perspective of one standing still and the other object is moving, but for the other object, it's the object standing still. So if you think, it's about like perspective. Yeah. I think I have I think for me, my struggle with these problems is that I have to figure out exactly how to implement the angles, and whichever angle you pick, you have to interpret that angle in a certain way. So I think that's the reason why with these problems I kind of have a little bit of trouble, because like I can implement the technique. The problem is that getting the correct angle, and putting my thought process on that. It was the tower that flew into the plane. Okay. So we have to have the plane, or at least the x component of the plane, match this. So now the question is it sine or cosine at this point? So we have a plane that's going 88.9 meters per second. And then we're leaving a space here because I know we're going to have to put a trig function here, like a cosine or a sine. And it has to equal, it has to equal 22 meters per second. Now I could have just left the units the way they are, but I don't want to like for me, I guess when I deal with physics problems, I just want to make it sure that it's at its appropriate units so I don't have to convert it later. Because the conversion is pretty easy. It's just dealing with all of it later is kind of like, I think, much better to handle than like doing it all during the problem. Okay, so now that we think about it, the x-coordinate is cosine, but we need the y component to be equivalent to this, but it has to be in the opposite direction, so it has to be northern of this. So I'm thinking it's going to be sine because we're going in the y direction. Now, so sine, but we have to remember we have to get the angles. So I think that's pretty easy though, because like when we get the angles, so let's say, because if we do tangent on both ways, so we'll just call this theta and we'll call this phi or phi. I always mispronounce it whenever I'm thinking about them. So if we do it from the perspective of the wind, and we think the wind is like sort of like, so we'll call this phi and we'll call this theta. So for theta, we have to think of it like this. So it's and then 22, because it's the opposite, and then 88.9. Because we got a choice between two angles. Yeah, I don't round it, so. Okay, and the other one is basically we're taking this way. So this one would be, oh no, this one would be the adjacent. Did I mix it up? Oh yeah, I did mix it up. So this is, so theta, so this is supposed to be theta right here. So this is fine because we took this one. So for theta, this is 75 degrees, or 7 point. Let's round it to 76, because it's like 75.97, so I'm like, yeah, we can round it up. Now, well, actually, let's just make this 14 degrees, because it's just like 14.0, so we'll just make it like that. Now, the thing is that which angle should we pick? I mean, the plane's angle compared to the wind is going this way, So if you think about it this way, let's put a, because the wind is coming in, so we can just make an imaginary line, and we'll just put this box here, because this angle would be equal to this angle if the plane was like up here, so this would be theta. So you would need the plane to like maneuver a little bit like this, like going like kind of like going like in this type of direction. And the wind is going in this direction. So we have to find a way to actually counter it. So I think it should be theta 76 degrees. Oh wait, you know what? I just like realized my my flaw in my thought, because it's not that we need to get that angle, we just need to get the angle from here, and like I'm totally like misconstruing my thought process. So we have to figure out what the angle is. So we have sine, then so we have to do sine. So 14.5 degrees. What direction should the pilot head? So we want so it should be 14.5 degrees, and the plane is going west. Yeah, it's flying due west, so 14 degrees north of west. I think that's basically what we need to do. So north of west. I think that's the direction we need to go. What is the speed of the plane over the ground illustrated with the vector diagram? So I just want to check this over, because if we have sine, then basically, because I know sine is basically for the y component, so I'm just trying to make sure that this works out, because if the plane moves this way, because we know we want to go against the wind, so the wind, so it's going to go this way. Now, I think when we actually have the angle, now we can actually get the magnitude of the plane's speed. So now we can actually use this equation. So let's just write what we have. So the plane is cosine of 14.5 degrees plus sine of 14.5 degrees J, and then we have the wind relative to the Earth. And that is just 22.2 meters per second. Oh, I'm not going to put the units because I didn't put the units for those two, so. I know I probably should put the units if I was in a course, but I'm like, we have a lot of writing already. So we want the plane relative to the Earth. Now, so when we think of the wind, I think it's just going to push down on the plane, so I think we're going to have to put a negative sign here because it's going to interrupt the flight path, because we want these to cancel so that this is actually the actual path it's going. So these two will definitely cancel, and then we're gonna have so the plane will be traveling 86.1 meters per second. Now if you convert that to kilometers per hour, so we have 1,000 kilometers, meters, it's supposed to be meters, and 1 kilometer, and for seconds, one hour. Yeah, that works. So times, then divided by 1,000. So that's 300 and I think we can put 310. I think 310 is like a good estimate because it's like 90, it's 0.96, so 310 kilometers per hour. And I think that's the main magnitude because these two are going to cancel out because it's just going to go straight. I mean, granted, it's going in a bit of an angle, but the wind is actually going to stabilize it, so it's not, it's going to actually like be straight. So hopefully that's the right approach. This is chapter 3, I believe. So we gotta go all the way down to problem number 38. I mean, hopefully we get this right. If not, then I still have a lot of work to do. Okay, here we go. So let's see here. Set up the equation. Okay. I mean, they kept the units the way they were, so like I think either way you're fine. Sine of 80. Okay, so our thought process was right. Okay. North of west, yes. Okay. And did we get the same answer? Yeah, we did. So what was the amount that they had? Was it just 14 degrees? Yeah, it was just 14 degrees, but we had 14.5, so it's pretty much close. Hey Single, how's it going? What's the best part of your day so far, my friend? So I guess we solved our first problem with relative velocity. Nice. Okay, so I have to like learn to slow down with these problems because I have to think about the angle and I have to think about what direction is what. So, like, what is it that we have to stabilize and what is it that has to be going forth? So, but I'm actually cool. We actually managed to get that problem right. I mean, I did get 14.5 degrees, but it didn't deviate from the answer we're supposed to get, so I'm pretty sure there's like a room for uncertainty there. So, yeah, I think that was a pretty good one. Just eating? What did you eat? I'm pretty sure it was delicious. Oh, this one goes off the page, so... let's take this first half. I don't know why my thing keeps doing that. It keeps doubling up. I don't know why it does that. And we have to take this bottom part. Okay. Paste. Cut. Can we line you up without breaking? It's like so close. Good enough. Just some fish dish. Oh, okay, I see. Well, at least you got something to eat. If I were to stream and I didn't have lunch before I stream, I would get a little bit hangry. So, you know, at least that was something to brighten up your day. Okay, what do we got? What is this problem? Canadian geese migrate essentially along a north-south direction for well over 1,000 kilometers in some cases. Traveling at speeds up to 100 kilometers per hour. If such a bird is flying at 100 kilometers per hour relative to the air, then there's a 40 kilometer wind blowing from west to east. So it's basically a wind that's going to east, the eastern direction. At what angle relative to the north and south direction should this bird head so that it will travel directly southward relative to the ground? Okay. How long will it take the bird to cover a ground distance of 500 kilometers from north to south? Even on cloudy nights, many birds can navigate using the Earth's magnetic field to fix the north and south direction. Interesting. I find it funny that they put that little note there, but I mean, if you're gonna get into like the study of like animals, mainly birds or like geese, I think that's probably good to like put in there, because science is basically like everything involving whatever subject you find meaningful. So, but then again, like, you know, like magnetic field is also part of physics, so that's something to keep in mind. Okay, so we have a Canadian beast. Canadian geese, not beast. Canadian geese. Make it sound like I'm talking about Bigfoot or the missing link. Migrate essentially along to north to south direction. So the velocity of the geese in the wind is, well, technically it's about the air, but you guys get what I mean. Kilometers per hour. And there is so this is the wind to the earth, 40 kilometers per hour. I should write the direction. So from north to south, aka just southern direction, and from west to east, mainly east. Okay. What is the angle relative to north to south direction should the bird? Okay, so alright, so if we draw this diagram, the bird is heading this way. The wind is blowing this way. And I don't think we have to convert the units. So, oops. I want to make sure I label it correctly. The geese to the wind, 100 kilometers per hour. Okay, so question A. So question A asks us at what angle. So angle relative to north to south. Direction. Should the birds head so that they will be traveling directly southward? Okay, so straight south path. Okay. We also have a wind blowing at the tail here, so I want to draw this a little bit so that way we have a I just put this line here so that way we're aware of like how it is. I'm not going to draw an arrowhead at the end because like I don't want to make it so it's like, oh, it's the wind's perspective or the geese perspective. So I think that would probably be good enough. Because I think what screws me up is that when I put an arrowhead at like either this end or this end, it interprets like either the geese or the wind. So I'm just leaving it there so we're not giving it any influence. At least for me, that's basically how I can interpret it. Because I think that's what gets me mixed up when picking angles. Okay, so I think when we think about this, the wind is blowing this way and the geese are going going southern, so it's going east. So we want the geese to actually have a west component where it's like it's going west, so it cancels out this. So we're gonna have, and then we're gonna have it equal to 40 because we want it to, so 40 kilometers per hour. I think we'll just erase this and then write 100 kilometers per hour, because right in here we're gonna have to determine the trigonometric function. So we have two angles. We have angle phi and angle theta. If I'm saying this angle incorrectly, because I don't know if it's phi or phi, like when you pronounce this, because I know there's two, because like I think these two, I always get these two mixed up. I think this one's phi and this one's phi. Like if anyone in the comments, I mean in the chat can correct me, please correct me if I'm saying it wrong. So now I have to determine which angle is the right one we should pick. So angle relative to north and south direction. So we have to figure out what the angle is. So, well, in order for the birds to maintain a southern direction, and if the wind is blowing east and they just go straight east, then if they go straight south like this, and the wind is blowing from the east, they're going to go off course a little bit. So they're more likely going to fly southwest. little bit. So I'm guessing this angle is going to be the main contributor here, because the geese are the ones that can move, but the wind can't move anywhere, it's everywhere. So mainly the geese are going to have to fold in this direction, if you guys can see my cursor. Because my thought process, if you guys can't see my cursor, is that the geese have to like fly towards this direction so that they can maintain a southern straight line. So it's gonna be this one. So be sine. Yeah, because they're going south, and basically this is still kind of considered the yeah, this is still considered kind of like the X direction here, because I think this is the reason why I would get mixed up, is because since the vectors are going in one going horizontal and one going vertical, I think that's when I get mixed up with the components, because we want this to actually like kind of like cancel this one out in some way, and like the only way to do that is just to change the direction of the X component here, if that makes any sense. And I'm trying to make sure that I say it out loud so like it makes sense to me, so that way like I don't jump the gun and just like assume like other things. Because this angle is going to be the determining factor of whether the geese go straight or whether the geese end up going in another direction like this way because of the wind. So I think this is the correct way to interpret it. So it'll be sine 40 kilometers per hour. Hopefully. I've always wondered, since their path is generally a curve, then why we calculate in straight lines. No, it's just that like they are going in straight lines. It's just that like the geese are going south directly, and the wind is blowing from east in the eastern direction directly. It's just that we want to maintain that the geese are going straight down south, and if the wind is blowing, then this the geese will end up like kind of like their flight path will kind of alternate like this way, because the wind is blowing them a little bit if they just go straight down. So they have to adjust for the wind pattern to make sure that they keep going straight, if that makes any sense. And that's why I'm actually like thinking this out loud. I mean, I'm not sure if I'm making sense myself, so apologies if I'm not making too much sense. Because I'm trying to actually make sure that I say this out loud so that I can better interpret it myself, so that way I'll be like, okay, like this is how it's supposed to be envisioned in my head. Because in order to overcome the wind being blown to the eastern direction, the birds, they have to actually alter their path a little bit. So they have to alter their path like in this direction, because they're flying this way, and there's no way they're gonna actually like shift side to side. So the only way they can do that is just like if they're going straight down and they want to go straight down and maintain this straight direction, like whether it be following the magnetic field or whatever, they have to actually like kind of shift themselves a little bit. I mean, that's the way I think of it. And hopefully my thought process is correct, and if it's not, then, you know, I learned something new that my thoughts are not interpreting. Hopefully this makes sense to you guys when I'm saying this out loud. Okay, how long will it take the birds to cover? Oh, I don't think you guys can see that. How long will it take the birds to cover a ground distance of 500 kilometers from north to south, even on cloudy nights? Okay, so we got a distance now. So now we gotta figure out a time. So velocity times time. All right, so we got an actual degree. So that means we actually have an angle, and then we actually have like the magnitude. So I think what they want us to do is actually like calculate all this relative to the Earth. Do we have to calculate the actual? Let's see, what is the relative angle? Okay, so I think like they assume that once we have all the parameters in check, then we have to add this. So we have to do the equation. Geese to the Earth is equal to geese to the wind plus the velocity of the wind to the Earth. Okay, so now the geese to the wind is 100 kilometers per hour times cosine of 23.6 degrees plus 100 kilometers per hour times sine of 23.6 degrees J, and then we have the wind to the Earth. That will be 40 kilometers, and it's just 40 kilometers east, so we don't have to worry about the angle there. Oh no, that's we have to do it from the x-axis. So it's I. Okay, and I think it has to be minus. Oh, you know what? Now that I'm seeing this, maybe... Maybe I used the wrong one. Cause let me think. I think I might have made a mistake here. Cause I remember sine is opposite over hypotenuse, and maybe it is cosine, because then because this is going from, because we want these two to cancel actually. Like we want these two to cancel out, because that way we don't have to worry about this side, and that way the geese can go straight. So maybe it is cosine. So let's just erase this for now. And yeah, because we want this to be 40 so that this is canceled out, and then this, it just maintains this direction. So I think it is cosine. So I think we gotta change the angle. So cosine. Yeah, because the way we line up the equations is going to be like this. And I'm just putting minus because we want the path here to be positive so that these cancel, and then we go straight here. So I think that's what we need to do. So cosine. So that leaves us with 64 degrees. 66.4, I should say. Yeah, because that's going to end up with 40 and these will cross out. And then we're left with the magnitude of geese to the earth. Then we have 100 times sine of 64.4 degrees. That gives us 90.6 kilometers per hour. So now that we have that, so now we have to, oh yeah, and we also have a distance that's 500 kilometers away. Was it kilometers? 500 kilometers, yep. So now we have to do the time, which is this. So if we do 500 kilometers divided by, we're left with 5.5 hours. Hopefully that is the right train of thought. Because I mean, this part kind of made more sense to me because I'm like, it's blowing in the X direction, and we want the X direction in here to be annihilated, so that we can get here, so we can get this to go away, and then this is just basically them going straight down south, which is what we want. And then thinking about it here, and like we got the numbers here, so I think it works out. Because then the magnitude is just this, so we don't have to do any fancy like square roots. At least I think so. So I think, so we have to write down what direction this is. So this is from, so if it's going this way, it's going to be south. It's going to be west of south. Yeah, west of south. So it has to be 66.4 degrees west of south. At least that's what I think it should be. So, okay, let's, hopefully we got this problem right. If not, then I'm gonna be like, wow, I am totally like, I mean, that's the hardest I've thought, so I feel as if like, I don't know if I can do better than that. Well, we got the time right, so I'm guessing, oh, they used the other angle. So, yeah, I think it's because I don't draw the diagrams correctly. Because the way they draw the diagrams is like, sometimes, I guess it's because it's from head to tail, and I don't do that. Maybe I have to draw head to tail more often. Because I noticed I don't do it like head to tail as often. Because I noticed that's what I've been doing with relative velocity. Because they use 24. use the hypotenuse? Because I mean, we got this one right. Like, how do they use the hypotenuse? Maybe the way they draw the hypotenuse. Because this is the air to the ground. This is from the birds to the air. And this is from the birds to the ground. Maybe it's the way I'm drawing them. Like, because, let's see here. This question... plane to the air, and the air to the earth. And then this is to the... yeah, because this one shows I'm guessing this is the wind, so the wind is blowing this way from the tip here. I mean... I mean, we did get the time right, so we must have done something right. Maybe this angle is just... because the thing of it is that we got a different angle. What did they did for this angle? Oh, they still use sine here. So I guess we were right in using sine, but... but I guess... because this is... so... Hey, Rushback. So I guess these problems are kind of like... a little bit... I think it depends on interpretation, because we still get the right answer down here. It's just that we got like the different angle because I kind of psyched myself out right here. Because I thought the point was just to cancel these two so that this is just left by itself. So, I mean, that's what we want, but at the same time, it's like, I think like interpreting the direction, like basically the path. So, this would be, because we wrote west to south, west of south here. What did they write? Is it the same? West of south, 24. Huh. I think it's just the relationship I'm not getting, because I'm like, yeah, because the southern direction's here, and then, I mean, we did get it right. It's just that we used a different angle to indicate it, and I think that's the one thing. I mean, it's not entirely wrong, but at the same time, it's like, how do I interpret this other angle? Because if you take 24 minus 24 plus 66, you probably will get, you will get 90. Because the reason why I'm making such a big deal is that, like, say if you were driving a plane, angles matter. So you have to know how to interpret the angles. It's not like I want to be a pilot or anything. It's just that I want to make sure that I know the facts correctly, or like how to interpret the data correctly. So if they say it's like 24 degrees west of south in their answer, then would my answer be south of west at that point? Because I mean, it makes sense. Why would that be the way it is? I mean, it did its job. It just basically annihilated that. So maybe like I have to stop thinking the way the textbook is trying to get me to think, and like I have to think about how to actually make this work. Maybe that's what I have to do. Because I think the thing that's kind of like making me confused is because I'm so used to like sine and cosine being like you know, the cosine is usually associated with the x-axis and the sine is with the y-axis. But in this they use sine here, and I know when I basically do this type of approach, like you would see like in algebra or linear algebra if you've taken those courses, I know that these two will have to cancel in order for this to remain by itself. So it's actually going in a straight line. But actually, Rushback, what's the best part of your day so far? I forgot to ask that because I was so deep in thought with this problem. So I feel like this problem, we didn't get entirely wrong, we just got the opposite way of thinking of it. So I think the reason why they do that is because they want you to get it from the south to the north perspective. And I think the perspective is the thing that's getting me a little bit off. Because right here, I mean, technically when you're given a problem, it's like, I think you have to answer it either way. So it's like, so this one's not west of south, it's basically south of west. So meaning it's from the wind's perspective in some way. Somewhat. Because usually when I think of the wind, it can either enhance the flight path or it can be a nuisance to it, and I think it would be a nuisance to it if it basically I put a minus sign here because I know it's going to be a nuisance to the birds if it flies down. So okay, I feel like I kind of learned a lot from that problem actually, because it's not entirely wrong, our approach, it's just that I think the direction of it was just off. We just got the direction of it off, like based on the interpretation of it, but I think we kind of got it. So I think like here's the thing, like the answer shows you this approach, and I'm guessing that's for like that. So I think for my reference is that I have to keep in mind there are two angles, and I have to basically ask myself which is the angle that I can go with, because if I'm using this data to solve this and we still got the same answer compared to like what they got here to calculate the time, I'm thinking that we did something partially right. It's just that we have to think of it in a different context. So I think that's the way I interpret it. So for me, if I'm doing these type of problems, I probably should keep in mind that there are two angles, and it's up to me which angle to pick. Because I notice with these type of problems, they make you choose sine a lot, and there's nothing wrong with that. It's just that I'm kind of like, it kind of just doesn't get my mind thinking, it gets my mind like completely flustered because I'm mixing up sine with like the x-axis and the y-axis, and I feel as if that I would probably more likely just want to calculate both angles instead of just fixate on just like keeping one algorithm for like one situation, if that makes any sense. Okay, so that's it for our relativity problem. So we did kind of better. We did kind of get this a little bit better actually. So I mean for me, so I think that's pretty good. Since we did a little bit good with those relative velocity problems, I thought we can actually get into some relativity, because like I kind of find it funny that I think the reason why they teach you just relative velocity is just so that you can interpret other people's point of view really early, because like it might be just important as other things in classic mechanics, but for me it always felt like it was kind of like out there, like it was just basically just there, and then suddenly you just forget it, and then you go into special relativity, and it's like, oh, now we actually have to think about an interpretation. So that's my That's my guess. Although I haven't read that much about special relativity, but it's like one of the subjects I want to cover for myself. So it's like, because I think it's cool. And I think that's where people start to love physics. Just like when you get into special relativity, you're like, oh, there's a lot of things like perspective and the speed of light and everything like that. For some reason, I want to highlight this. Oh, no, don't do that. Because it's about to chop off the 8, and I don't want it to do that, so... Then we just paste that here. The reason why I'm copying it is because, sometimes I remember the speed of light, like its exact number, but then, I always end up forgetting to write it, so... to simplify it, I want to be able to remember its simplification, and I always forget the exponent. So, let's see, we got, like, the one thing I don't understand is why didn't they put his first postulate in, like, a yellow box? The laws of physics are the same in every initial reference frame. The speed of light in a vacuum is the same in all inertial frames of reference and is independent of motion of the source. And I think the reason why they put that there is because if you're traveling in a car and you have the headlights on, the light from the headlights is still going at the speed of light, regardless of how fast the car's going. Because if the car's going and you have like light coming from the headlights, most people would actually have to add those. But then what Maxwell discovered is that either Maxwell or Faraday, I think it was Maxwell, like if anyone knows like physics history, like please correct me if I'm like completely incorrect. They discovered that light travels the same speed in every reference frame, and I think that conflicted with like some ideas with Newton when it came to like motion. So it was like that was something that Einstein kind of unpacked once he was thinking about the question. Okay, let's see. Yeah, so I think this is explaining the behavior. So Newtonian mechanics makes correct predictions about relativity, slow-moving objects in A, which is like this. So if we have a space station that's going... So yeah, you would have to add the speeds together because they're going in the same direction. But then when it comes to light, this doesn't occur. Because actually nothing travels faster than the speed of light, which is kind of strange. Yeah, Newtonian mechanics fail. Newtonian mechanics tells us incorrectly that the light moves at a speed greater than the speed of light relative to the Earth, which contradicts Einstein's second postulate. So when you're thinking about like, I guess like, it's kind of funny because like physicists and mathematicians, even though they deal with two different things, it's so interesting how their logic is built on like the same way that mathematicians build axioms. So, you know, I find that very interesting. But of course, it's no surprise. This is the reason why math is part of STEM, because like the way the mathematicians structure their thoughts is probably similar to the way scientists build rules. Well, I shouldn't say rules, like maybe scientific laws and theories. The ultimate speed limits. It is impossible for an initial observer to travel at c the speed of light in a vacuum. Okay. Galilean coordinate transformation. So choose your initial frame coordinates wisely. Many of the equations derived in this chapter are true only if you define your initial frame of reference as stated in the preceding paragraph. For instance, the positive x direction must be the direction in which the origin prime moves relative to the original origin. Okay, so, oh, they show us a figure here. So the position of particle P can be described by the coordinate x and y in the reference, in the frame of reference of S, or by x prime and y prime in S prime. Okay. So let's see how this is. So this is y prime and x prime. Oh, okay. I was about to say, are they connected? So that's y and u. Okay, so x prime is basically, I think u is supposed to be some random number. Is that a u? Yeah, it's a u. I thought it was a v for a second. I was like, wait. Okay, so that's basically according to the transformation. Now here's the fundamental problem. Applying the speed of light in a vacuum in the equation that the speed of light is like Einstein's postulate supported subsequently by a wealth of experimental evidence that says that c is equal to c prime. This is a genuine inconsistent, not an illusion, and it demands resolution. If we accept this postulate, we're forced to conclude that that these equations, which one's the second one? This one, cannot be precisely correct despite our convincing derivation. These equations have to be modified to bring them into harmony in this principle. Okay. In our kinematic concepts, the idea of the assumption of the observers, and so. Okay. Relativity of simultaneity. Oh, didn't mean to do that. What happened? Let's go back. Relativity, where was it? Was it length? Here? Simultaneity, okay, here it is. Let's see, measured times and time intervals involve the concept of simultaneity. In a given frame of reference, an event is an occurrence that has a definite position and time. When you say you woke up at 7 o'clock, you mean that two events, your awakening and the clock showing 7, occurred simultaneously. Okay. So this is time dilation. We'll probably need this. So they also call it gamma, so I think we can copy this one too, actually. So that we can have it, because sometimes they can just give you gamma and As a further simplification, u over s is sometimes given the symbol beta. Okay, so it would be like 1 minus beta. Okay. I mean, sure. I might encounter that in a book one day, so that's good to know. I mean, it would make the formula look cooler, actually. Okay, we use the term proper time to describe the time interval, okay, between two events, okay. Alright, so now we have our first problem. So let's see if we can do this, because I think the first time I did this I ended up not doing it correctly, because I wasn't thinking of it correctly. So let's try it. Let's try this example. Okay, high energy subatomic particles coming from space interact with atoms in the Earth's upper atmosphere, in some cases producing unstable particles called muons. A muon decays into other particles with a mean lifetime of 2.2 microseconds. Okay, good. They made the conversion for us. That makes so much easier. As a measure in a reference frame in which it is at rest. If a muon is moving at 9.990 C relative to the Earth, what will the observer on Earth measure its lifetime to be at? So we have time is equal to measured as a frame of reference, so I'm thinking this is the proper time. And V in this case is 0.990 C. So if we put that in the equation we have for time, so the proper time 1 times giving us, so if we put the numbers in, because I think we can just plug, so times 10 to the negative 6 power over square root of 1 minus 0.990 to the square. We have the time at 1.6. Well, actually they gave us like around 2 significant figures, so I think what we can do is just make it 5, 6 times 10 to the negative 5 seconds. I mean, it's a very minuscule change, but it's not 0. Let's see, what will the observer on Earth measure its mean lifetime to be? Yeah, that's what we got, because they did it in, I think that's microseconds. So yeah, it's pretty much simple. That was a simple one. Now let's see the other one. I think this one was the one I kind of got a little bit error in thought with. So let's see if we can do it again, because I don't remember the answer or the method how to solve it. So let's see if we can think carefully about this one. Okay, an airplane flies from San Francisco to New York. Okay, so we have a distance of 4,800 kilometers. I'm so glad that they converted the units, because I'm like, it's like, I don't have time to convert units. No, that's probably a lazy way to think. It's like, units, I don't have time to convert the units. Come on, give me the actual SI units, please. Steady rate of meters per second. How much time does the trip take as measured by an observer on the ground and by an observer on a plane? Okay. So for the observer on the ground, their time would be this. We also have the proper time, which is up here from the person in the plane. V squared. So I think we can just take the gamma factor here. And I think for the ground it's much easier because we have because we're not doing accelerated motion. So we can just basically calculate the time that way. If it's going at a steady speed of 300 meters per second, and then basically take the distance. So we can basically take that as the actual time. And so we'll have, so the time, I think we can just write this as the proper time here. Well, not the proper time, but the time of the observer on the ground. That might help us. And then when we calculate gamma, we can basically use gamma to get the proper time. So the time difference is gamma times the proper time. So if we have this, then we can basically make the proper time equal to gamma. That's supposed to be a gamma, not a gamma over the time there. So no, what am I doing? So just do this, velocity squared, and then so we'll calculate gamma. So 1 over the square root of 1 minus, and now we gotta do 300 squared over 3.00 times 3 to the 10th, no, 3 to the, to 10 to the 8th power squared. I want to make sure that I type these correctly, so. Okay. Then. Delete that. That is fine. And wow, so gamma is just 1 at that point. Well, it makes sense because it's not traveling faster than the speed of light, so so basically both of them are the same time actually. So if you take meter to 4.80 times 10 to the 6 meters and divide that by 300 meters per second, you're left with 16,000 seconds. So the person in the plane is going to experience the same amount of time because gamma is not altering anything. So the observer is going to experience the same passage of time as the one on the plane. Excuse me. Sorry about that, guys. I just want to make sure I double check with the gamma factor, because the last thing I want to do is get the wrong answer. So it's always good to check, because sometimes I don't check and I end up paying for the consequences for that. Times 10 times 3 to the 10 times 10 to the 8th power. Okay, it is still equal to 1. Okay, so both. So at that point, so the proper time did I put the equation right? Yeah, it's gamma. So the proper time is going to be 1 over. Oh, maybe that's the difference. So like that's how much time is kind of changing between the two. Okay, so I think that's the thing we have to get used to special relativity, is that this is not just the time. This is not time. It's basically how much time has passed. I think that's basically what, or the differences, I should say. The differences in the times from the observer to the... So, if you were to minus 16,000 minus 116, that's practically like 15,999.999. It's practically almost close, but it's not zero. It's like the difference is very minuscule, actually. Yeah, we got the same answer there. Yeah, I think like with me, whenever I try to do problems and I look at the answer, sometimes the answers are they get the answer in a different way, and my brain doesn't like compute it because it's something different than what I would do. And like whenever I try to figure out the way they do it, if I struggle too much on how they get it, I try to find it in a different way that is more close to the way my brain kind of processes it. So I think that's basically the thing that when you're like learning, it's hard to get used to that. Like you end up questioning the answer more than you question your thought process. If you feel like it doesn't match with what your brain kind of wants to naturally interpret. And I think that's why people struggle with certain like schoolwork, because it's they feel like they have to interpret it in the way that the book says it, instead of trying to find their own path to actually interpret it in the way their brain is like more accustomed to. And I think like the more you study and the more you observe like different ways of getting the answer, you realize, oh wait, like even though I accept the fact that the way that they got the answer is probably the right one, my way to get it there is probably something that I have to work up to. And I think that's the thing that is really hard for when people are studying and they get stuck at a brick wall at the end, like when they're trying to figure stuff out. Okay, so what is this next one? Just when it is proper. Mavis boards a spaceship and zips past Stanley on Earth at a relative speed of okay. At the instant she passes him, they both start timers. A short time later, Stanley measures that Mavis has traveled 9 times 10 to the 7th power meters beyond him and is passing a space station. What does Stanley's timer read as she passes the space station? Okay, so the distance she traveled is what does Stanley's timer read as she passes the space station? And what does Mavis's timer read? Stanley starts to blink just as Mavis flies past him, and Mavis measures that the blink takes. Oh, okay. So this one is like asking so many questions. So so we have to figure out what the time is between the two. Alright. So the thing that we can calculate from this, we can calculate gamma, which is this. And the speed of lights are going to cancel, and this is going to be squared. So gamma, in this case, is going to be 1 over the square root of 1 minus 0.600 squared. That gives us 1.25. And then we also have the time, gamma, and the proper time. So that we have in mind. Now, given the speed and the distance, so we have to calculate the time it took. So at this point, it would be the distance over the velocity. And we have a little bit of the speed of light there, so we're going to have to include that. So let's actually calculate that. So 9.0010 to the 7 divided by 0.600 times 3 times 10 to the 8th power. So that's a half a second. Wow. Okay. So according to Stanley would read a half a second, and for Mavis, I mean, the time difference there is that so 1 times a half a second. I don't know. It's supposed to be, so it'll be 1 over. So the proper time in this case is like that. Okay. So that over half a second, that leaves us with 2 seconds. So for Mavis, it felt like it was 2 seconds, but for Stanley, it felt like half a second. Well, that's because he's traveling at the speed of light, which is fast. Very fast. Yeah, right now I'm just basically interpreting the data because I'm like, for Stanley, that's Stanley's still, right? Let's see. Then zips past Stanley on Earth. Okay. Relative to the speed at an instant passes him. Both start a timer. The short time Stanley measures, Mavis traveled. Okay, beyond his. What does this reader? So it's half a second for him, and then it's like practically 2 seconds for her, 2.5 seconds for her. Stanley starts to blink just as Mavis flies past him, and Mavis measures that the blink takes for. Okay, so let me just do that, and then for B. So Stanley blinks, so the time she reads is from the beginning to the end. According to Stanley, what is the duration of his blink? Okay. So technically there's like a 2-second like delay between the two, because from Mavis's perspective, she is practically like she's 2 seconds ahead of well, and from her perspective, 2 seconds like faster than Stanley. So Stanley measured a half a second, and she measured 2.5 seconds from her perspective. So from her perspective, it's so if gamma is 25 and then we multiply that with so practically he just blinked in that half second. It's just like a half a second for him. I think that's how the answers are gotten, but let's see. I could be wrong, so let's take a look. Takes a half a second, right? Let me see if I did this right. Because I think I did not do that right. Let me see what I missed. So we got this right. Maybe this is timer. So this isn't right. This one's a fraction and this one is like basically this will go down. I guess like for this one, like it's not like that one is wrong, it's just that I think the way I was thinking about it was not the way it should be interpreted. Because that actually makes sense, but it's like, because the way they did it was like this. But I don't know why it turned out that way. And times. Let me see if I typed gamma right. Maybe I should put parentheses around the square root. That's what it is. So I have to keep in mind that this is equal to this. So in this case, this I can multiply by which gives us a half second, which means like he just blinked as soon as she passes him. Let's see, the start and finish of Stanley's blink occurs at the same point in his frame of reference, but different position in Mavis's perspective. So the interval is that she measures between the events equal to the time difference. Oh, okay, so these time parameters are like based on depending upon who's who. Okay. So for her, this is her frame of reference, and the proper time for, so it depends on who's the proper time is for, depending upon who's measuring. So that's something to remember. Then that leaves us with 0.32 seconds. Okay, so to keep in mind, depending upon who's measuring what, we have to make sure that these two are delta t and delta t naught. I think we have to make sure, or at least I do, have to make sure that these are meant for So this one's meant for like, I guess the one that's observing and the one that's being observed. So I think that depends on the perspective there. So, oh yeah, the twin paradox. I think we've heard that story many times. Or that thought experiment, I should say. Relatively length. Oh, okay. Alright, so relativity of length. Not only does the time interval between two events depend on the observer's frame of reference, but the distance between 2 points may also depend. So 2 times the, let's see, it's length in this frame, okay? Okay, length contraction. So we'll definitely take this equation, put it right here. So that's the actual length, and this is the length of what the person observes. And the velocity, oh, okay, so it's practically gamma. Okay, a length measured in the frame in which the body is at rest is the proper length. Thus, the proper length of this, and then this is the effective length contraction. Okay, so now we're given another problem. Alright. Let's see. How long is a spaceship? A spaceship flies past Earth at a speed of, okay. A crew boards on the spaceship, measures its length, and obtains the value 4 meters. What length do the observers measure on Earth? Okay, so I'm guessing that's their interpretation, so I think L naught is supposed to be 4. The C's will cross out, so we're left with so I think this one shouldn't be too difficult. So 50.4 meters. Wow. Well, then again, you're going at this like close to the speed of light, so that's a big reduction. very interesting indeed. To think that something like that long could actually be reduced to something this size. That's crazy. Okay, so we have another one. Oh, we have a figure. Figure. I mean, it doesn't have to be that big. Probably could make it like this. Alright, how far apart are observers? Oh, okay. Observer 1 and observer 2. And 2 observers on Earth simultaneously attain the length of... Oh, okay. So... So the 2 observers in figure are 56.4 meters apart from Earth. How far apart does the spaceship and the crew measure them to be? Oh, okay. Hey, Sasha. We're learning. I don't know what you mean by winning, but we're learning. But what's the best part of your day so far, Sasha? How are your classes going? Does this take, is this like part of the example of, I'm guessing it is because there's not much in this problem. Sorry about that, guys. That was the answering machine. Like, my parents still have a landline, and we couldn't connect it anywhere else until, like, because apparently our landline links, they're all, like, I think they're broken except for, like, connecting it to the main modem. That's why you heard that. Luckily, we basically just turn off the ring, but, like, unfortunately, the answer machine, I don't know how to, like, turn that down. And it's usually just spam callers. I'm like, oh my gosh. Like, now it's just robots. Completed 1 homework? Nice. See, that's a win. Okay. Alright, so I'm guessing we're supposed to take the same problem like last time, so... Now, Earth, okay. The observers are apart from Earth. Apart on Earth. How far apart does the space crew measure them to be? So does that mean we have to do the exact same thing, only with the numbers switched? There was a cool question involving octernions. Is that what you typed up? Oh no, not octernions. Oh, okay. Isn't that like supposed to be the extension of a vector? Like, I mean, a vector that has multiple directions in some way? Because I've heard of octernions. Although I don't know what's the difference between an octernion and a tensor. I've heard of quaternions. I just Oh, you wrote octernions. Like I've never heard of octernions, but I've heard of quaternions. Yeah. Yeah, I don't know the difference between what an octernion compared to a tensor. So, all right. So, let's see. So is it the same premise? Do we just take the length of what they measure of the space station and just apply it to? So let's say that this is. Wait, hold on. Let me just see how I solve this one. Oh, I don't know why I wrote a knot there. It should be just a regular L. So let's just say that is that, and then L is still the same, where it's like and instead of 400 meters, maybe we can do it this way. Was it 9? Yeah, 9 squared. 560 times 1 minus 0, 0. So they measure them to be 7, 9, 6 meters apart. Two observers are apart, so is that the measurement they got? Yep, that's the same one. Okay, so I was right in my way of thinking. Cool. So basically it's a vector space where you can multiply vectors together that satisfies certain conditions. The usual example are complex numbers, quaternions, and octernions. For quaternions, the multiplication may not be commutative in general. You don't have x times y is equal to y times x. Okay. For octernions, you may no longer have associativity. Oh, okay. Interesting. Very interesting indeed, actually. Actually, when do you start learning about quaternions and octernions? So parentheses are a nightmare. Fair enough, fair enough. Ooh, Lorentz transformations. How objects move near C would appear. So basically, if you're traveling at the speed of light, you would probably seem kind of squish, because you're going so fast. Okay, Lorentz transformations. First question is this: when an event occurs on x, y, and z at time t, as the observer and frame reference s, what coordinate system is x prime, y prime, and z prime, and t prime of the event observed by s prime? Okay. To derive the coordinate transformation, we refer to the figure. right here. Oh, here we go. This is much more. I like it when everything is in boxes, so I can just like do this. Whatever you want. For me, they are more a novelty. Oh, okay. I guess you can define the exceptional Lie group G2 using octarions, so it has application. Oh, okay, I see. Yeah, actually, like getting back to like math proofs, right? Like I've been trying to find like a book or like lecture notes on like the relationship you taught me, Sascha. Like why is it that two negative numbers would make a positive number? I've been like I could probably skim through like our previous like lecture videos, or at least the lecture videos that you gave me, that you taught me when we started during the summer. Like I'm still trying to figure out. I'm trying to find notes on like how to better like articulate the relationship between that, because I know it has something to do with equivalence relations, and then I remember we were talking about rings at that point. Yeah, because I think like with equivalence classes, we were able to prove that subtraction exists, I believe. But whenever I look at the equivalence relations, equivalence classes in like books and the books that I have currently, I don't see anything about like, you know, how to introduce subtraction or division. And I think like the notes that I saw online, from what I got so far, they don't fully go into detail. Like they would show you like, I think the equivalence class quotient relation, but I don't think they cover like it in excruciating detail. Oh, there's a lot of stuff here. Velocity, Lorentz transformations of velocity. So what's the difference between these two? Oh, this is velocity prime. Okay, so take this. Like so. And then we'll also take this one. Alright. Okay, so this one is for so basically it's for different observers. That's what these are for. I probably might have to read more on these, but I'll probably do that during the week. But I believe that will finish it for today's stream, guys. Thanks for joining me today. If you like math and physics, or you just need a study stream to keep yourself productive while you're at your computer, or probably like doing your studies like in between classes if you're in the library or something, you know, if you're watching this on YouTube Live, consider dropping a sub, in addition to leave a comment down below, as well as like the video. If you're or like the stream, like if you're watching this live already. If you're on Twitch, you know, consider dropping a follow if you like math and physics, or you just need a study stream to keep yourself productive during your times of just basically doing your homework, or basically doing any projects you're doing online, or like coding or whatever it is that you're doing on the computer, or maybe through your phone. I'm not sure. But thank you for joining me today, guys. It's been a lot of fun. We probably will do more physics problems next week. Maybe we'll practice more on like special relativity, because since we already kind of got started on it. I will definitely study more on special relativity during the week because this is what we left off on. And yeah, so I think that will be about it. So thank you for joining me today, guys, and always remember, oh yeah, before I forget, we also have our Discord server, which popped up in the Discord chat. All the links will be in the description down below if you're watching this on YouTube. I almost forgot to mention that. So, and also my video game channel is also down there. So, but for Twitch, I will also post my video game channel if you want to attend my video game channel, like just to chat with me, just to hang out with me while I play video games. But yeah, so as I was gonna say, always remember, guys, everyone is precious. You guys are just as precious as everyone else. And I will see you guys in the next stream. So see you guys next week. Take care, guys. Bye-byes.